The answer is not just about the size of your EV battery. It depends on how much electricity your home uses, how often you drive, how fast your charger is, how much sun your roof gets, and whether you have a home battery. In this video, we'll break it down in a simple, practical way, so you can calculate the right solar system size for your own situation and avoid the most common mistake people make when adding an EV to a solar home. Number 1. Start with the real problem. The question is not simply, how many solar panels do I need for an electric car? The real question is, how much energy do I use at home? How much energy does my EV need? And can my solar system produce that energy at the right time of day? That difference matters because an EV is one of the biggest electrical loads most homes will ever add. A normal house might use around 10 to 25 kilowatt hours of electricity per day, depending on heating, cooling, cooking, hot water, appliances, and how many people live there. But an EV can easily add another 10, 20, 30, or even more kilowatt hours on the days you charge it. A kilowatt is the speed of energy use. A kilowatt hour is the amount of energy used over time. So if your EV charger pulls 7 kilowatts for 3 hours, that is about 21 kilowatt hours. That one charging session can be similar to the entire daily electricity use of a house. This is why some people install solar panels, buy an EV, and then feel disappointed. The solar system may be fine for the house, but not large enough for the house and the car together. Or it may generate enough energy across the whole day, but not enough power at the exact time the car is charging. So the first thing to understand is this. You are not sizing solar panels for the EV alone. You are sizing a system for your full daily lifestyle. That includes the house, the car, the battery if you have one, cloudy days, seasonal changes, roof direction, shading, and the limits of your inverter and charger. For many EV owners, a small solar system can still reduce the bill. But if your goal is to charge mostly from solar or get close to a zero electricity bill, you usually need a much larger system than people expect. A 5 kilowatt solar system may help. A 10 kilowatt system may cover many homes. But once you add regular EV charging, a system around 12 to 15 kilowatts, or sometimes even larger, can make much more sense if your roof and local rules allow it. Number 2. Calculate your daily energy need. The easiest way to start is with your electricity bill. Look at the last 12 months, not just 1 month. Your summer and winter numbers may be very different, especially if you use air conditioning, electric heating, heat pumps, electric hot water, or pool equipment. Find your daily household usage. Some bills show this clearly as average daily kilowatt hours. If your bill only shows total kilowatt hours for the billing period, divide that number by the number of days on the bill. For example, if you used 600 kilowatt hours over 30 days, your average is 20 kilowatt hours per day. Now separate your normal home use from your EV use. If you do not already own an EV, estimate it from your driving. A practical average for many EVs is around 15 to 20 kilowatt hours for every 100 kilometers, or around 25 to 35 kilowatt hours for every 100 miles. The exact number depends on the car, speed, weather, tire pressure, hills, and driving style. Here is a simple example. Let's say your home uses 20 kilowatt hours per day. Your EV needs another 20 kilowatt hours on a charging day. That means your total demand on that day is around 40 kilowatt hours. If your home battery also needs to be filled for night use, your solar system has to produce enough for the house, enough for the car, and enough extra to charge the battery. This is where many people make the first mistake. They only think about the car battery size. They say, my EV has a 70 kilowatt hour battery, so I need 70 kilowatt hours of solar every day. That is usually not how people actually charge. Most drivers do not empty the car to zero. and charge it to full every day. They top it up. Maybe they charge from 30% to 70%. Maybe they add 20 kilowatt hours every few days. Maybe they only need 10 kilowatt hours after a normal commute. So do not size your system based only on the full EV battery. Size it based on how much energy you realistically need to replace. If your car uses about 15 kilowatt hours per day from driving, then that is your EV energy target. If you only charge twice a week and add 40 kilowatt hours each time, then your charging days will be heavy, and your solar system needs to handle those bigger days. A useful planning method is to write 3 numbers. First, your normal home use on a mild day. Second, your home use on a high-demand day with heating or cooling. Third, your EV charging energy on the days you plug in. Once you have those numbers, the solar size question becomes much clearer. Number 3, understand charger speed. Energy is only half of the problem. Power at the moment of charging is the other half. A common home EV charger may charge at 7 kilowatts. That means, while the car is charging, it wants 7 kilowatts continuously. If it runs for 3 hours, that is around 21 kilowatt hours. If it runs for 6 hours, that is around 42 kilowatt hours. Now imagine your solar system is generating 8 kilowatts at that moment. Your house is using 2 kilowatts because people are home. The fridge is running, the air conditioner is on, and maybe the washing machine is running. That leaves about 6 kilowatts available for the car. If your charger is set to solar-only mode, it may reduce charging speed because there is not enough spare solar power to give the car the full 7 kilowatts. If the clouds pass over and solar production drops to 4 kilowatts, the house may still need 2 kilowatts. Now, only 2 kilowatts are left for the EV. The charger may slow down a lot, pause, or use battery power if your system allows it. If you allow grid charging, the grid can fill the gap. But if your goal is to avoid buying electricity, then your solar system needs enough extra generation during the charging window. This is the main reason a larger solar array helps. You may think, my EV charger is only 7 kilowatts, so 7 kilowatts of solar panels should be enough. In real life, that is usually not enough. Solar panels rarely produce their full rated output for long periods. Your house is using power at the same time. Clouds reduce output. Heat reduces efficiency. Roof direction changes production throughout the day. Shading can reduce production. And if you want to charge a home battery at the same time, you need even more surplus. A more practical target is this. If you want to charge an EV at 7 kilowatts from solar and still run the house, you may want peak solar production around 12 to 14 kilowatts during good sun. That does not mean every person needs 14 kilowatts. It means that for a solar-only charging experience at full speed, especially with a battery system, a larger array gives you much more breathing room. In the best case, your panels may generate 14 kilowatts in strong sun. The EV takes 7 kilowatts. The house takes 1 to 2 kilowatts. The extra 5 or 6 kilowatts can charge the home battery. That is the ideal situation, because the car charges, the house runs, and the battery prepares for the evening. In a weaker situation, your panels may generate only 5 or 6 kilowatts. The house takes 2 kilowatts. The car only gets 3 or 4 kilowatts. The car still charges, but slower. A 3-hour charging session may no longer add 21 kilowatt hours. It may add only 9 to 12 kilowatt hours. That may be fine for a short commute, but not enough if you need a large top-up. Number 4, convert system size into panel count. Once you know the solar system size you want, calculating the number of panels is simple. Take the target solar size in watts and divide it by the wattage of each panel. For example, 14 kilowatts is 14,000 watts. If each panel is 450 watts, 14,000 divided by 450 gives about 31 panels. If each panel is 400 watts, you need about 35 panels. If each panel is 500 watts, you need about 28 panels. That is the clean math. But real installation is not always that clean. Your roof may not fit that many panels. Some roof areas may be too small, too shaded, too steep, or facing the wrong direction. There may be vents, skylights, antennas, chimneys, or roof edges that reduce usable space. Your electrical rules may limit how large your system can be. Your inverter may have a maximum solar input limit. Your installer may need to split panels into different groups facing different directions. Panel direction also matters. In the Northern Hemisphere, south-facing panels usually produce the strongest total output. In the Southern Hemisphere, north-facing panels usually do best. East-facing panels produce more in the morning. West-facing panels produce more in the afternoon. East and west panels can still be very useful, especially if you charge the EV during those times, but they may not hit the same peak output as the best-facing roof. This is why the rated size of the solar system is not the same as real output. A 14 kilowatt solar array does not mean you will always see 14 kilowatts. It means the panels are rated for that under test conditions. In real life, output changes every minute. Heat is another factor. Solar panels like sunlight, but they do not like extreme heat. On a very hot day, production can drop compared with the panel rating. Dirt, dust, bird droppings, and tree debris can also reduce output. Shade is especially important. Even partial shade on a panel can reduce performance, depending on the panel design and system design. Modern panels often handle partial shading better than older panels, and systems with optimizers or microinverters can reduce the impact of one shaded panel on the rest of the system. But shading is still not something to ignore. Before installing, check the roof at different times of day. Look for shadows from trees, nearby buildings, chimneys, antennas, pipes, and other roof equipment. A roof that looks perfect at noon might be shaded badly in the afternoon. So the practical answer is not just install 30 panels. The answer is choose your target system size, calculate the panel count, then check whether your roof can actually deliver that output during the hours when you need EV charging. Number 5. Match panels, inverter, and battery. A common question is, why would someone install 14 kilowatts of solar panels with a 10 kilowatt inverter? That can sound wrong at first, but it can make sense. Solar panels produce DC electricity. Most homes use AC electricity. The inverter converts DC from the panels into AC for your house, your grid export, and many AC EV chargers. When people say they have a 10 kilowatt inverter, they usually mean the inverter can convert up to around 10 kilowatts of power into AC at one time, depending on the system design. But the solar panel array can sometimes be larger than the inverter rating. This is often called oversizing the solar array. The reason is simple. Panels do not produce their maximum rating all day. If you have a 10 kilowatt inverter and exactly 10 kilowatts of panels, you may only hit high output for a short time, and on cloudy or imperfect days, you may be far below it. If you install more panel capacity, the inverter can reach strong output more often and for longer periods. With a home battery, the design can be even more interesting. Some systems can send DC power from the panels into the battery without converting all of it into AC first. In that situation, the inverter may be powering the house and the EV charger on the AC side, while extra solar energy charges the battery on the DC side. The exact behavior depends on the system, so this is something your installer must confirm for your equipment. This is also why the EV charger type matters. A 7 kilowatt AC charger uses AC power. That means solar. DC power must be converted through the inverter before the charger uses it. A DC charger works differently and may connect more directly with the battery or solar system, depending on the product. Most homes use ACEV charging because it is simpler and cheaper, but the limits still matter. Before choosing your system, ask your installer a few direct questions. What is the maximum solar panel size allowed with this inverter? What is the maximum AC output? Can the system charge the battery and power the EV charger at the same time? What happens when solar production drops below the charger demand? Will the charger slow down, pause, pull from the battery, or pull from the grid? Can I set solar-only charging? Can I set a minimum battery reserve so the car does not drain the home battery before night? That last point is important. Without the right settings, your EV can accidentally use energy you wanted to save for the evening. For example, you may think the car is charging from free solar, but if clouds come in, the system may start draining the home battery. Later at night, the home battery is low, and your house buys power from the grid. Technically, the car charged during the day, but the whole home system did not work the way you want it. A good setup should match your priorities. If your priority is the lowest bill, you may allow the charger to use solar first, then battery, then cheap off-peak grid power. If your priority is grid independence, you may prefer solar-only charging and a strong battery reserve. If your priority is always having the EV ready, you may allow grid charging when needed. There is no single best setting for everyone. Number 6, choose the right size for your situation. Here is a practical way to decide how many solar panels you actually need. Start with your normal household energy use. Let's say it is 15 kilowatt hours per day during mild seasons and 25 kilowatt hours per day during hot or cold seasons. Then estimate your EV charging. If you add around 20 kilowatt hours on charging days, your total demand may be 35 to 45 kilowatt hours on those days. Now compare that with expected solar production, not just panel size. A 10 kilowatt solar system might produce plenty on a perfect sunny day, but far less during cloudy weather or winter. A 14 kilowatt system gives you a better chance of covering the house, charging the EV, and charging a home battery, but it still will not guarantee perfect results every day. A realistic planning target for many EV households is to install as much good quality solar as the roof, budget, rules, and inverter design can reasonably support. If you only drive a little and charge slowly during sunny hours, you may not need a huge system. If you drive a lot, charge often, run air conditioning, and want solar-only EV charging, you should plan for a larger system. For a light EV user, a smaller solar system may still work. If you only need 5 to 10 kilowatt hours for the car on most days, and you can charge during the middle of the day, even a modest system can help a lot. You might not charge fully from solar every time, but you can reduce grid use. For a medium EV user, where the car needs around 15 to 20 kilowatt hours several times per week, a system around 10 to 14 kilowatts can be much more comfortable if the roof has good sun. This gives the system enough output to run the house and still send meaningful power to the EV. For a heavy EV user, where the car needs 30 kilowatt hours or more on many days, solar-only charging becomes harder. You may need a large solar system, smart charging, a battery, off-peak grid backup, or all of these together. In that case, the best setup is usually not just bigger panels. It is bigger panels plus smart control. The most common mistakes are easy to avoid. Do not size the system using only the EV battery capacity. Do not assume the solar system will produce its full rating all day. Do not forget the house is using power while the car charges. Do not ignore roof direction and shading. Do not install a charger without understanding how it behaves when solar output changes. And do not let the EV drain your home battery unless that is what you actually want. Before installation, check your last 12 months of electricity usage, your daily driving distance, your charger power, your roof space, your roof direction, shading, inverter limits, battery size, and local solar export rules. Ask your installer for an expected production chart by month, not just a total yearly number. The month-by-month view matters because winter production can be much lower than summer production. After installation, do not judge the system from one sunny day. Watch it over several weeks. Check how much solar is produced, how much the home uses, how much the EV receives, how much goes into the battery, and how much still comes from the grid. Then adjust charging times and settings. Often the best improvement is not hardware. It is simply moving EV charging into the strongest solar window and lowering the charger speed when full speed is not needed. So the practical answer is this. If you want to charge an EV from solar, first calculate your home use, then calculate your real EV energy need. Then choose enough solar to cover both during your best charging hours. For many people using a 7 kilowatt home charger, a system around 14 kilowatts is a strong target because it gives enough power to charge the EV, run the house, and still support a home battery in good sun. But the exact panel count depends on panel wattage. With 450 watt panels, 14 kilowatts is about 31 panels. With 400 watt panels, it is about 35 panels. With 500 watt panels, it is about 28 panels. The final check is simple. Your panels must produce enough total energy across the day and enough spare power during the hours your EV is plugged in. If both are true, solar EV charging feels easy. If only one is true, the system may still save money, but the car will charge slower, use the battery, or pull power from the grid whenever the sun is not strong enough.